Container with most water. So we are given an array of integers, and each integer represents height of a wall, or a wall of a certain height of that many units. And we have to return the volume of the largest container defined by two of these walls, right? Such that those two walls, if you were to flood everything inside with water, ignoring every walls that kind of happen to be inside. So imagine they don't exist. There are no walls inside. So if you fill this container to the brim without tilting the container, so the lower wall will be filled to the brim, and then there will be, if the other wall is higher, it won't be full to the brim. So that volume should be maximum, as high as possible, and we have to return that volume, right? That's what we have to return. Okay, let's start thinking about this algorithm. So an algorithm, a trivial algorithm would be, we could examine every possible container, every possible pair of walls, right? Measure the volume and just select the maximum. So that would give us O(n) squared, order of n squared number of operations. So our time complexity would be O(n) squared. Probably not the best. The best, absolutely best, would be O(n). I mean, we cannot do any better than that. We don't know at this point that O(n) does exist, but we can be sure that nothing better than O(n) exists, right? Because you have to touch at every wall, roughly every wall, right? So for example, even if you ignore two walls, they could be so tall, even if they just stand right next to each other, still they could be so tall that they define volume, which is just incredibly large, and it's bigger than anything else, right? So you cannot skip even two walls. So that means you have to examine roughly every wall. That's your O(n) right there. So let's start by looking for an algorithm that has O(n), order of n operations, right? Now, we can easily say that the wider the container along the x-axis, the better. I mean, everything else being equal, wider containers are better, right? And everything else means height. So if everything else is equal, the wider containers are better. So why don't we start with the widest possible container? Yeah, the widest. So set left here and right here, and that would be our widest container. So we can have its volume calculated, not hard, and we'll call this the best volume so far, okay? Now, we're going to be moving these walls inwards. We're going to try to move these walls inwards. But whether we move this wall left or this wall right, we want to be sure that we don't ever have to come back to this wall ever again. Okay? That is basically what's going to guarantee that the complexity will be O(n). Because if we have to come back, that means we could easily go back to O(n) squared, right? So we don't want to come back ever again to this wall. So if we're going to abandon a wall, either wall, we better ensure that this wall cannot be part of a better container, right? So let's now think about, so this kind of gives us some sort of outline of our algorithm now. So imagine the following. Now. So let's say we're keeping track of the best volume that we've encountered so far, right? And currently we're looking, let's say, at some container, I don't know, maybe this one. So our left and right are pointing to this, okay? So this is left and this is right. So we're in the middle of our algorithm somewhere. That's kind of useful to say what's going to happen in the middle of the algorithm at some iteration of our loop. Now, I want to ensure at every point that if a better volume exists than whatever we've memorized, right, then a container like this definitely does not have walls outside of whatever we're looking at. So I have to assume that my algorithm is such that if I've managed to narrow down left and right to this type of range, then at the very minimum, if a better container exists, better than this volume that I've memorized, then none of its walls are outside, okay? If I can ensure that, that's great. And initially, obviously, when I initially start my algorithm, that's given because I'm looking at the widest possible, I mean, I'm looking at the entire array. So if a better container exists, better than this, then clearly its walls cannot be outside of the array. So I can be guaranteed that my kind of logic is fulfilled initially. But now, when I move one of those walls, I must keep that guarantee, because when I abandon one of these walls, I must ensure that this wall is also not part of a better container, of a more voluminous container. And then my algorithm should just perpetuate itself, right? Then basically it will work by induction. Now, if I abandon a lower wall out of these two walls, right? That should be, we can easily prove that that wall, the non-taller wall, the lower wall, is never going to be part of a better container. How do we prove that? Well, we know that what's going on here is whatever volume we have memorized, it's at least this volume that we have here. At least, right? Because this is the volume of the currently largest container we've seen, and that includes whatever we are currently looking at, right? So if a better container has this wall as one of its walls, then its height obviously cannot be taller than the height of the current container. But the width will definitely be lower because, I mean, if I abandon this wall, all other walls outside are excluded. So the pair, its like counterpart of the other wall will be also somewhere inside. At best, it's this one. So the new container, the height cannot go higher, but the width definitely goes down. So the volume will also go down. There is no way that a better container has this as a wall, right? Provided that I came to this place correctly so that, as we said, all of the other walls outside are also correctly excluded. Then I can abandon the lower wall or non-higher wall, move to the next wall, and be sure that this wall is also one of those that is not part of a better container, right? All right, this looks absolutely horrible. But I think we have an idea how to tackle this problem now. At least I have an idea. So I'll try to implement this, right? So pretty much we keep the volume, which is the currently best volume, and we look at left and right. And those walls that are currently lower, in the sense that it's not higher than the other, we can move this inwards. until these walls actually meet. So until left is strictly less than right. Yeah, because when they meet, when left is exactly equal right, that means volume is 0, and that's the end of our search. Let's try to implement this now. I'm going to move to a different editor here. This is typescriptlang.org. So typescriptlanguage.org. Typescriptlang.org, right? So we said we're going to do left equals 0, right equals height length. That sounds weird. Height length. Length of the height array minus 1, right? And then let our volume be, what is the volume? So that would be right minus left, correct? Multiplied by height, multiplied by the minimum value of height at right and height at left. So the minimum value of that, right? That's our minimum value. So that would be height of the container, and that would be the width. This is the width of the container along the x-axis. So now we are ready to go into the loop. Now, first of all, that means we have what? If we have 0 elements, what's going to happen here? This will be minus 1. So this will be, so we have to have at least 1 element. Do we have that assurance? We have at least 2 walls. So technically, we need some sort of assurance that at least we have at least 1 wall. For 1 wall, this is fine because left and right will be looking at the same element. This is 0, and 0 times minimum, this is basically either one because these are the same. So for 1 wall, this is fine. For 0 walls, this is not fine. So technically, we would check if there is at least 1 wall, but let's not do it because we have that assurance. Now let's go into the loop, right? Before, while left is less than right, that's what we said, right? Now, what should we do is basically, this is what we said. We are going to move the lowest wall inwards. Okay, just look at the picture. So the lowest wall, if this is the lowest wall, we're going to move it inwards. And how should we do it? So if height of left is less than height of right, that means the left wall is strictly lower. So we should do plus left. Otherwise means right wall is not higher, definitely. It could be the same as left, but at least it's not higher. So that gives us the opportunity to reduce right. So move right inwards to the left. Yeah. Now, we need to recalculate volume. A new volume would be what? It would be basically the same thing, right? Let's call it constant V1. That's our new volume, right? So new right or new left, whatever is. Yeah, that's new volume. And now let's say volume equals maximum of volume and V1. Why V1? I mean, just call it V. I mean, we can have a better name here. So you don't even need this variable. Obviously, you can just put this whole huge thing here, or you can have a function or something that calculates this volume. Let's keep it like that. So once we exit this while, we can confidently return volume and be sure that this is the best possible volume. Let's try now our solution here. Okay. Let's run this on the pre-tests. See what happens. Okay, pre-tests were passed. Why don't we submit this to the full suite of tests and see what happens? Okay, that worked. It's a decent solution, right? I mean, obviously, it's a solution, first of all. We got accepted. And we beat 75% of solution. So it's ON. I mean, the complexity is absolutely fine. We are actually doing ON, and it's the coefficient of ON in terms of, I mean, ON, there are different types of ONs, right? It could be the coefficient in front of N could be different. So this is a decent solution, if you ask me. So I'm pretty happy with it.